the image impedances and iterative impedances, and we derived these relations for a T network, that was Z A plus Z C by Z B plus Z C into sigma Z A Z B. This means combination of two impedances at a time. So, it was a structure like this, Z A, Z B C, and this was Z B. Similarly, Z I 2 we derived as Z B plus Z C divided by Z A plus Z C into sigma Z A Z B. This we derived last time. We also derived for the iterative impedances Z T 1 as half of Z A minus Z B plus under root Z A minus Z B whole squared plus 4 times that sigma term Z A Z B. Similarly, Z 2 was Z T 2 was half Z B minus Z A plus Z A minus Z B whole squared, the same expression. Okay. Then we discussed about a network that is a lattice network where we considered Z A, Z B, Z A, this was the notation, for the counterparts. This is Z B and this is Z A. This can also be seen as a bridge network like this. This was say Z B, Z A, Z A, Z B, and these are the output terminals 2, 2 dashed, 1, 1 dashed. And for this kind of a symmetric network, we saw this Z naught, the characteristic impedance was Z A and Z B product. Okay. Also for the T network, we saw if it is a symmetric T network, for a symmetric T network, Z I 1 is equal to Z I 2 is equal to Z T 1 is equal to Z T 2. By symmetric T network, I mean Z A is equal to Z B, and that was equal to Z naught. Okay. And then that relation becomes very simple. You can see from here itself, Z A plus Z C, Z B plus Z C, they will be getting cancelled. So, you will be left with only Z A Z B product. So, that gives me the product as Z A Z C plus Z A Z C plus Z A squared, that is equal to Z A squared plus twice Z A Z C. Now, if I have a network, a balanced network where the impedances are like this, a symmetric network like this, Z 1 by 2, Z 1 by 2 and Z 2, then Z A is Z 1 by 2, this is also Z1 by 2. So, this will become Z1 squared by 4 plus 2 into Z1 by 2 into Z2. So, this will be Z1 Z2. One may write this as root over of Z1 Z2 into 1 plus Z1 by 4 Z2. This we saw last time. For a pi network, one may derive this. For a pi network, similarly, well, we have also seen if this side is loaded by the characteristic impedance Z naught, then if this is a sending end current, this is a receiving end current. We also established a relation between I s by I r in a logarithmic scale. This was defined as a quantity p, which is basically representing the ratio by which the current falls, okay, in a logarithmic scale, and that was shown to be log of I s by I r to the base p, and this was x plus root over of x squared minus 1. This kind of expression we got, where x is 1 plus Z1 by twice Z2. Okay. So, this expression that we got last time gave me cos of p is equal to x, and that is equal to 1 plus Z1 by twice Z2. Let us see for a pi network what will be the situation. For a pi network, similarly, we can go by the short circuit and open circuit test. Short circuit and open circuit impedances are evaluated, and you can get the characteristic impedance. What will be the characteristic impedance? If I call it Z naught pi, this is the impedance Z naught pi. The impedance seen from this side is also Z naught pi. What is that Z naught pi? So, Z naught pi will be perform the short circuit and open circuit impedances you evaluate from there, and that will be Z open circuit into Z short circuit. So, if I short this, it will be twice Z2 in parallel with Z naught Z naught pi, sorry, in series with Z1, again the combination in parallel with this. So, it is 2 Z2 in parallel with Z1 plus parallel combination of twice Z2 into Z naught pi by twice Z2 plus Z naught pi. Okay. This is the short circuit impedance. Open circuit impedance will be twice Z2 in parallel with Z1 plus twice Z2. Okay. So, twice Z2 in parallel with Z1 plus twice Z2. So, this is the open circuit parameter. Open circuit impedance, short circuit impedance, take the product and evaluate this. Z naught pi, you have to change sides and then make all kinds of manipulations, you can get the result. I leave it to you as an exercise. Finally, you can verify for yourself. This will boil down to, it is a very interesting expression, Z1 Z2 divided by 1 plus Z1 by 4 Z2. Interestingly, you see, for a T network it is Z1 Z2 into 1 plus Z1 by 4 Z2 under root. Here it is square root of Z1 Z2 divided by the same factor. You see, this is dimensionless. So, it is something little more than 1. You are multiplying once, in the other case you are dividing. So, if I take the product, you can see Z O T multiplied by Z O pi will be product of these two, that will be Z1 Z2. This is also very interesting result. Now, let us see what will be the ratio that we saw last time, the ratio of the current in a logarithmic scale. What will be this value in case of a pi network? So, once again, in case of a pi network, if I take this as the receiving end current, this as the sending end current, suppose this intermediate current is some I 1, then how much is IR in terms of I 1? Let us evaluate that. IR in terms of I 1, it will be I 1 multiplied by twice Z 2 divided by the total impedance. So, twice Z 2 divided by twice Z 2 plus Z naught pi. Is that all right? And once again, I 1 is what kind of share this current will have from I s. It will be I s multiplied by this impedance twice Z 2 divided by the total impedance, which is twice Z 2 plus Z 1 plus parallel combination of these two. So, twice Z 2 plus Z 1 plus twice Z 2 Z naught pi by twice Z 2 plus Z naught pi. So, this fraction of I s is I 1, then that gets multiplied by this factor to give you the total current. Is that okay? So, I s by I r, if one evaluates, I am not going into the details, I s by I r if one evaluates and and computes the logarithmic in the logarithmic scale, the propagation, this will be equal to log of twice Z 2 plus, after all reductions, it will, you have to substitute the value of Z naught pi, which you have already got Z 1 Z 2 by 1 plus Z 1 by 4 Z 2 under root. So, you have to substitute there, and then after simplification it boils down to Z 1 Z 2 into 1 plus how much, Z 1 by twice Z 2 or 4 Z 2. You check up, Z 1 by 4 Z 2 divided by Z 2. Okay. So, this once again gives me an expression similar to, if I assume this to be x plus x square minus 1. So, the expressions are identical whether it is a pi network or a T network, and once again we get cos p. If you take the exponential of that, that gives me this is equal to p. So, if you take e to the power p is so much, all right, e to the power p is x plus root over of x square minus 1, whence we get cos p is equal to x, and x is this quantity 1 plus Z 1 by twice Z 2. Okay. So, so far we have derived the conditions, we have derived the relation between the two currents when the network is terminated by the characteristic impedance. In both the cases, that is a T network or a pi network, of course symmetrical network. Now, from this point we bring the concept of a filter. Before we go to that, I will just briefly explain what this quantity P means. This P was log of I s by I r. Now, this unit is after the name of the mathematician Napier, the name of the unit is Napa. Mind you, this is a dimensionless quantity, it is just a logarithmic quantity. It refers to the current gain or current loss, you can say, how current propagates, how it gets diminished or reflected by this ratio when the network is terminated by the characteristic impedance. Now, in any network, if we take the ratio of the power, P 1 is the power that is pumped into the circuit, P 2 is the power that is extracted at the receiving end, then it will be equal to, if it is compared with the same, say if the current is flowing through the same resistance, say 1 ohm, then it will be proportional to I s by I r squared. Okay. That is voltage gain or current gain if you know, then square of that will be the power gain. Okay. Mind you, this is power P 1, P 2 etcetera, whereas this P refers to only the ratio, this logarithmic ratio. Now, we define, we have already done in Bode plot, when we talk about voltage gain or current gain, I s by I r log of that with the base 10 was the unit bell, okay, and 10 times that was decibel. Okay. So, you take smaller units, smaller denomination to define a unit. Now, what will be the relationship between decibel and Napa? Now, you see, Napa is okay, let us see, log of P 1 by P 2 is log of I s by I r. I am extremely sorry, the ratio of power when you take the logarithm with the base 10 and you take a denomination of 10, then that becomes the unit of that becomes decibel, all right. The unit is decibel. If this 10 is not there, it is bell. So, bell is basically logarithm of the ratio of power, and logarithm of ratio of current or voltage we are defining as Napa. So, log of P 1 by P 2 to the base 10 is log of I s by I r to the base 10 squared. So, it is 2 log of I s by I r to the base 10, and if one changes this to 2 into log of I s by I r to the base e, then this will be multiplied by log of 10 to the base e. Okay. Suppose the number of units in Napa for such a ratio is n, then say the ratio P 1 by P 2 is say x. Okay. Okay. I s by I r is x. So, if it is x, then log of x to the base e will be 2.303 log of x to the base 10, okay, and 2n is therefore 2.303 log of P 1 by P 2 to the base 10. Should we take okay, I am extremely sorry, I was starting with this ratio P 1 by P 2. So, if P 1 by P 2 is x, then it will be simply like this. So, this will be 2.303 to the base this is in decibel. So, d by 10. Okay. So, n into, if you take this 10 on this side 2.303, if you divide n into 8.686 will be the number of units in decibel, okay, where d is the number of units in decibel for that same quantity. That means 1 Napa is equal to 8.686 decibel. Mind you, n is the number of units. So, if the number of units is small, okay, then multiply by 8.686 you get number of units in decibel. It is like 1 rupee corresponds to 100 paise. So, paise is a smaller denomination, but then number of units will be more for a coin if we take say 100 1 paise coin. So, number of units will be 100, the value of that coin is less. 1 rupee, it is just a single one coin, that will be representing a higher denomination. Okay. So, if the denomination is higher, number of units will be less. So, n multiplied by 8.686 will be equal to d. It is something like rupee multiplied by 100, you get 100 coins. So, the value of d is very very small. So, 1 paise, if you multiply by 100 by this number, then only you get 1 rupee. It means that. So, 1 Napa is equal to 8.686 decibel. I hope this point is clear. Now, again we will come back to the relationship that we have derived. Cos p is equal to x, that was 1 plus z 1 by twice z 2. Okay. So, we will start from this point. We will start from this point for going into the design of a filter. Now, what does a filter do? In a filter, there are, let us have a very basic elementary idea about the filter that we are going to discuss now. Filter is a network which will be allowing, say this is the gain, some of the frequencies present in the signal to pass through unattenuated, there is no attenuation, there is no change, and rest of the frequencies are arrested, they are not allowed to go. This is the case of an ideal filter, ideal low pass filter. An ideal filter will have a constant gain in the pass band, this is the pass band, and it has a 0 gain in the stop band. Similarly, a high pass filter, an ideal high pass filter will have gain characteristics like this. This frequency we call a cutoff frequency. So, beyond this cutoff frequency the gain is uniform 1, and before that it is not allowed to pass through. So, this is a high pass filter. Similarly, we also have a band pass filter, that is certain band is allowed FC1, FC2, this is a band pass filter, and we also have a band gap or band reject filter, that is frequencies below FC1 will be allowed to go, will be allowed to pass through. Similarly, frequencies above FC2 will be allowed. So, this is the pass band, this is the pass band, and this is the stop band. Okay. So, this is band reject filter or band stop filter. If in this band stop filter, if you have this gap very narrow, almost like this, then it is a notch filter. Similarly, if it is allowed only in this narrow band, this is an inverted notch. Okay. Now, we will see what this factor P means. P may be a complex quantity. When you are taking the ratio IS by IR in a complex network, this may have a phase, this may have a phase. So, this is a complex network. So, the logarithm of that also may be a complex quantity, means the current magnitude changes, its phase is also changing. So, let that complex factor be alpha plus j beta. That means, IS by IR is basically e to the power alpha plus j beta, which means e to the power alpha, this is the magnitude part, and e to the power j beta. What does it mean? IS is equal to e to the power alpha times IR in magnitude. So, the receiving end current gets multiplied by e to the power alpha to give you the magnitude of IS, and with a phase shift of beta. So, the receiving end current, if you multiply a factor e to the power j beta, if you give a phase shift, then only you will get IS, the angle associated with IS. So, P is equal to alpha plus j beta. What is cos alpha plus j beta? We have seen cos P is equal to x. This is cos P, this is cos P. So, that is equal to x, and that was 1 plus Z1 by twice Z2. Now, our filter design starts from this point onward. Now, from the discussion on what exactly the filter is supposed to do, we have seen the filter is basically supposed to allow a certain band of frequency unattenuated. So, for the low pass filter, if you consider, if I consider alpha, when alpha is 0, this is 1, that means the ratio of the current is 1, current is not suffering any change in magnitude. So, for alpha, this value up to F c should be 0, and then ideally speaking it should be going to 0 value, there should not be any current received, and hence IS by IR will tend to infinity. Ideally, this should be the characteristics of low pass filter. Similarly, for the high pass filter, we should have alpha very large up to F c, and then it should be 0. Okay. So, this is high pass filter. This will not be allowed, this is the forbidden zone, this is the pass band. You can draw similar characteristics for band pass and band reject filter. So, let us come to the expression for the cos p term. This is 1 plus Z1 by twice Z2. This means cos hyperbolic alpha cos beta plus j times sin alpha sin beta is equal to 1 plus Z1 by twice Z2. Now, let us assume that Z1 and Z2 are lossless. That means, when we are transmitting a signal, through the network, there is no loss in the network, all right. Power is directly given to the load. So, Z1 and Z2 are lossless reactive element. Okay. So, this will be, they may be of the same type, they may be of the opposite type, we will study. If Z1 by twice Z2, this is, both of them are reactive, then this will be a real quantity. So, this whole expression is real. So, the imaginary part is 0. Therefore, 1 plus Z1 by twice Z2 is real. Therefore, sin alpha multiplied by sin beta is 0. So, there are two possibilities, either this is 0 or this is 0. Okay. So, we will take up one at a time. Case 1, when sin alpha is 0, that means alpha is equal to 0. So, this is the pass band, we have just now seen. When alpha is equal to 0, it is a pass band. Here alpha is 0. So, this is the pass band, this is the stop band. So, this corresponds to the pass band. Okay. Now, for sin alpha to be 0, that is alpha to be 0, what are the conditions on Z1, Z2? So, sin alpha is 0. So, cos alpha is 1. So, here cos alpha into cos beta, cos alpha is 1. So, cos beta is equal to 1 plus Z1 by twice Z2. Therefore, cos beta is equal to 1 plus Z1 by twice Z2. Okay. But cos beta in magnitude cannot be more than 1. That means, we know cos beta must lie between plus 1 and minus 1, is it not? So, that means 1 plus Z1 by twice Z2, 1 plus Z1 by twice Z2 should lie between minus 1 and plus 1. So, minus 1, 1 plus Z1 by twice Z2 should be 1. Subtract 1 from all of them, that gives me minus 2, Z1 by twice Z2 is equal to 0, which means if I further divide by 1, minus 1 Z1 by 4 Z2 0. What does it mean? It means from 0, if I take Z1 by 4 Z2, this ratio, then it should lie between 0 and minus 1. Z1 by 4 Z2 should lie between 0 and minus 1, then this is the pass band. Here only alpha is equal to 0. Okay. Let us take the second case. When sin beta is equal to 0. So, this is the pass band. When sin beta is equal to 0, there are two possibilities, beta can be 0 or plus minus pi. Now, first case, if beta is 0, that is sin beta is 0, then cos beta is equal to 1. Therefore, cos alpha becomes 1 plus Z 1 by twice Z 2. Now, cos alpha is always a positive quantity, is it not? E to the power alpha plus e to the power minus alpha by 2, you put any value of alpha, fraction, integer, anything, it will be always positive, more than 1, this is also more than 1. So, added together divided by 2 is also greater than 1, is always greater than equal to 1 when it is equal to 1 when alpha is equal to 0. So, cos alpha which is greater than 1 should be 1 plus, you have got cos alpha is equal to 1 plus Z 1 by twice Z 2. So, Z 1 by twice Z 2 must be positive, which means Z 1 and Z 2 are of the same type. If they are of the same type of reactances, then there will be definitely some value of alpha other than 0, that means there will be attenuation. Okay. So, if we have Z 1 and Z 2, if Z 1 and Z 2 are of same nature, that is both are inductive or both are capacitive, are of same nature of reactances, then alpha is not equal to 0, hence there will be attenuation. So, it will be in the stop band. An ideal filter will have infinite attenuation. If there is some attenuation, it will not be the pass band. Now, in the second case, we have beta is equal to plus minus pi. So, cos beta is minus 1. Therefore, minus cos alpha is equal to 1 plus Z 1 by twice Z 2. Now, this quantity you can see from here, cos alpha is therefore minus of 1 plus Z 1 by twice Z 2. This can be realized only when this quantity is highly negative, so that this plus 1 is swamped out and the overall quantity becomes plus. Okay. So, this needs, since this is always positive, so Z 1 by twice Z 2, Z 1 by twice Z 2 you can see for yourself must be less than minus 2. That means, Z 1 by 4 Z 2 must be less than equal to minus 1. So, that will be giving me alpha not equal to 0 and beta will have a value of plus minus pi. So, Z 1 by 4 Z 2 less than minus 1, this is the region where beta will be plus minus pi, and this is the stop band, this is the forbidden region. And here also, when both of them are positive, both of them are of the same nature, the ratio is positive, this is also a stop band. Okay. So, this is what we have got now. Now, what about Z naught? How will that change? Now, the characteristic impedance of the filter will be either real or imaginary. It cannot be in between, it cannot be just a complex number. Either in the pass band it is alpha equal to 0, or in the stop band it will be very large, but beta will be having a phase shift of either 0 or plus minus pi in the two regions, in the two stop bands. In the case of purely reactive elements, say Z A or Z 1 and Z 2, purely reactive, then you do not get a situation when this will be complex. that is the ideal situation. So, Z naught, let us see the characteristic impedance Z naught and P propagation constant. These cannot be adjusted independently. You cannot adjust them independently, one is dependent on the other, can be adjusted independently. This is a very important point. Now, let us see how beta varies. Beta was 0 here, this is minus 1, this is Z 1 by 4 Z 2, and here sorry alpha was 0 here, beta was 0 here, somewhere here it was say pi, it will be, we will see later on how these characteristics will change. It will be something like this, at minus 0.5 beta will be pi by 2, this is pi. Okay. So, this is beta. Now, we will go for the design of a constant K filter. Constant K filter. Let us take two elements, say Z 1 is j omega L, just an inductance, that means we have L by 2 and then L by 2 and a capacitance C here. Z 2 is equal to minus j by omega C. Okay. What will be the characteristic impedance for this? We are considering for the time being only a T network, we can also see for the pi network. So, Z O T is root over of Z 1 Z 2 plus Z 1 squared by 4, and Z 1 Z 2, if you take the product Z 1 into Z 2, it is omega L multiplied by 1 by omega C. So, L by C, okay, root over of L by C plus Z 1 squared by 4 will be giving me minus omega square L squared by 4. Okay. Now, if the product Z 1 Z 2 is taken, Z 1 Z 2 is L by C, we define this as a constant K filter, means it is totally resistive. So, this constant is having a ohmic value, R k is some defined in terms of ohms. So, this is known as a constant K filter design when we take Z 1 Z 2 as the product R k, and we call this a prototype design. There can be other derived filters from this prototype. So, L by C. So, this gives me root over of R k square, or okay, I can take L by C outside, then 1 minus omega square L by C is R k square. So, this will be L C by 4. Okay. When omega square L C by 4 equal to 1, this becomes 0. Okay. The reactance becomes 0, and this frequency we call omega C is therefore 1 by 4 by L C under root, which is 2 by root L C. Corresponding radian frequency to hertz, if we convert, this will become 1 by pi root L C, so many hertz. We have got two equations. L by C is R k squared and root L C is 1 by pi f c. So, we may be given a specification in terms of the cutoff frequency f c and the constant R k. If you are given these two values as a filter specification, then we can calculate L and C. Just take the product, that gives me L, if you take L C. So, L C, it will be pi f c squared. Then if you take the product, it will become L squared is equal to R k squared by pi f c squared, whence L will become R k by pi f c. Okay. And similarly, by eliminating L, C can be determined from any of the equations into f c. So, normally the specifications are given in terms of this constant impedance and f c. So, Z O T therefore comes out as, which was given as L by C 1 minus omega square L C by 4. I can write this as L by C is Z 1 Z 2 or R k squared. So, this is R k into 1 minus omega squared L C by 4. If you look at it, L C by 4 was 1 by omega c, so squared. So, with respect to frequency, it will start when omega is 0, it is R k from this value, and it will gradually fall like this. Okay. So, the characteristic equation does not remain constant as such, it varies with the frequency in this manner. This is for a T network Z O T. One may derive similarly for a pi network the situation is like this. You have C by 2, C by 2. Okay. So, for a pi network, what will be the values of Z naught? Z naught, you know, is root over of Z 1 Z 2 divided by 1 plus Z 1 by 4 Z 2. So, substitute for this, Z 1 Z 2 is the same product, okay, which will be R k, and 1 plus Z 1 by 4 Z 2, once again by the same logic, if you substitute for Z 1 j omega L, for Z 2 1 by j omega c minus j by omega c, okay, that gives me 1 minus omega square L c by 4, which is again written as 1 minus omega square by omega c square. So, when omega is very small, this is R k. When omega is very large up to omega c, when omega is omega c, this becomes 1. So, 1 minus 1 is 0. So, this becomes infinity. So, it will be shooting up at this frequency, it will go to infinity, it will be approaching infinity. Mind you, when you go beyond omega c, it becomes imaginary, both the cases, it becomes imaginary. So, the characteristic impedance switches over from a real quantity to an imaginary quantity. Okay. That means you cannot transmit power. Imaginary means the load impedance is imaginary, so you cannot transmit any power, as simple as that. Now, if you have, instead of inductance, if you have capacitance in the series and inductance in parallel, this arrangement, then what you get? Z1 and Z2, they have interchanged their elements type. So, this becomes omega c, Z2 becomes j omega L. So, Z O T, I will just write the expression for the T network, which is Z1 squared by 4 plus Z1 Z2. Okay. That gives me root over of L by C into, if you permit me to simplify, 4 omega square L C. Okay. So, when 4 omega square L C, this becomes equal to 1, that is omega square is 1 by 4 L C, corresponding frequency we call it omega c, then this becomes how much? When omega square c, omega c squared is equal to 1 by 4 L C, that is this whole quantity is 1. So, 1 minus 1 is 0. So, Z O T is 0. So, here at this frequency it is 0, and when omega is very very large, this becomes almost 0, it is root L by C. So, it will be tending towards R k, root L by C is R k. So, from F c onward, you can write F c or omega c, either you take F or omega axis. So, it will become, it will tend to R k. We will stop here for today, we will continue with this in the next class. Thank you very much. Okay, good morning friends. Last time we discussed about the properties of impedance, characteristic impedance, and today we will continue that and discuss about design of filters. Now, we saw last time cosine beta was 1 plus Z1 by twice Z2 when alpha equal to 0, that is in the pass band. This means because beta is cosine beta is between minus 1 and plus 1. So, we can write minus 1 plus Z1 by twice Z2 less than equal to 1. If I subtract 1 from all the 3, then it reduces to Z1 by 4 Z2 less than equal to 0. Okay. Now, in the stop band, we have where alpha is not equal to 0, we put the other condition sin beta sin hyperbolic alpha equal to 0. Okay. That means, there are two possibilities. If sin beta equal to 0, then beta can be either 0 or plus minus pi. If beta is 0, then cos hyperbolic alpha, that is cos alpha is 1 plus Z1 by twice Z2, and if beta equal to plus minus pi, then minus cos alpha equal to 1 plus Z1 by twice Z2. this we saw last time. So, from here we can find, if I take Z1 by 4 Z2 along this x axis, then between 0 and minus 1 of this is a pass band, and beta will be varying like this. So, in the pass band that R k, okay, and F c, this was a relation. So, it will be 600 by 4 pi into 10 to the power 4, so many Henries. Okay. Similarly, capacitance will be 1 by 4 pi k into F c, that is 1 by 4 pi into 10 to the power 4 into 600, so many farads. Okay. Suppose you are asked to calculate, let us take another example, you are asked to calculate for a T section low pass filter, determine the frequency for which alpha, frequency f for which alpha is equal to 10 dB, f in terms of f c, frequency f in terms of f c. So, alpha is given as 10 dB, that is 10 by 8.696. If you remember, we discussed earlier the relationship between dB and Napa. So, that comes to approximately 1.15 Napa. So, alpha is equal to twice cos inverse f by f c, that is 1.15 is twice cos inverse f by f c. Okay. So, from here you can see f will be f c into cos inverse 1.15 by 2, 1.15 by 2. So, this is the relationship between f and f c at this frequency, at this value of alpha. Okay. So, we will stop here for today, and next time we will be taking up some more basic elements of graph theory, how to solve network problems with the help of graph theory. Thank you very much.